Good evening and welcome to the live session for the course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you.
అలాగా
ఉమ్. మరి ఈవేళ చేసుకుని ఉంచుకుంటే రేపు పనికి వస్తుంది.
ఎంతకంటే తేదీ కుర్రోడు వేవు కుర్రోడు వేవు
కుర్రోడిదే ఇక్కడ గోపాల్ ఫ్రెండ్.
All right, we're ready to start. Once again, good evening and welcome to the live sessions for the course on fundamentals of additive manufacturing technologies. This is week 12 of the live sessions, and the course is taught by Professor Sajin Kapil, who is a member in the faculty in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So the course contents for this week dealt primarily with electron beam based powder bed AM and binder based powder bed AM. So we'll look, those are the topics we'll be talking about today. And for the first set of lectures, it had to do with electron beam powder bed AM, the working principles and the subsystems, the process cycle, powder, including powder manufacturing technologies, the scanning systems, common challenges, and interaction of the beam and powder. And based on Professor Kapil's categorization, we have been dealing with AM processes based on the type of feedstock being used. Uh, the last module has been dealing with powder additive manufacturing or processes that have a powder as the material feedstock. As you already know, such processes can be divided into either a powder bed additive manufacturing type processes where the powder is already available in the form of a bed. For each successive layer that is reprinted, the powder is recoated and the region is suitably scanned, say either with a beam like an electron beam or a laser beam, or as we will see later today, using a binder. The other type is the powder feed additive manufacturing, such as the blown powdered active energy deposition process, where the powder, where the laser scanning head scans over the regions of interest, and the powder is selectively dispersed in those regions only, rather than being available throughout the possible printing area and being removed later. Now, among the powder bed AM type processes, you have already looked at the energy beam based processes. That is, we have looked at the laser beam powder bed process. Today, we'll be talking about the electron beam based powder bed AM, and also later today about the binder based powder bed AM. So, here is a general schematic of what is commonly called the electron beam melting process or the EBM process. This is one of the commonly used names for this electron beam based powder bed additive manufacturing process. Also, although there are certain differences in the sense that the powder is really top fed instead of being bottom fed as shown here. But in other aspects, it is pretty similar to what laser beam based powder bed AM process would look like. So you have a reservoir of powder, whether it is being fed from the bottom or the top, and a recoater. In the case of laser, we saw that recoater can either be like a blade, or it can be like a roller, or it can be like a slot fed mechanism. But in the case of electron beam based powder bed AM, it is mostly a doctor's blade or a recoater blade. The other technologies have not really been explored to that a great extent. And here the energy source or the scanning source is in the form of an electron beam. That is, rather than being a beam made up of photons, now we have electrons in their place. Electrons, as we know, they transfer energy uh, to the substrate or to the layer to be deposited by virtue of their uh, low mass and high velocities. That is, they transfer kinetic energy for the purpose of melting of the powders. Also, as we can see, just like the laser beam based powder bed AM processes, the explicit support structures need not be always required, as the surrounding loose powder will act as a support. However, in cases where we fear that there might be warpage of the parts, in such cases we may have to engineer some explicit support structures, and then again, it is not to prevent that overhanging structure from, say, under the action of gravity to fall down, but rather it is to prevent them from warping upwards and colliding with the recoater blade or some other part of the machine. The joining mechanism in this case will be melting only. So sintering is seldom used. In fact, I am not aware of any published research where they have resorted to just sintering. Mostly it's melting. Powder material for EBM is metallic, so metals, and that is because for the electron beam to get channeled through and the electrons to get deposited, the powder should be conductive, and typically that is the case with metals. The scanning system uses electrostatic and magnetic coils, as we will see. The powder delivery system, as we discussed, is mostly top fed, but a bottom fed mechanism is also possible. The recording system, also, as we discussed, is typically just composed of a doctor's blade or a recorder blade. The other technologies such as uh, roller-based or slot-fed powder recording systems are not really explored. The built atmosphere will consist of a vacuum, and just to recall why this is a vacuum and not, say, any inert gas purged environment, is because electrons are very light particles, one of the lightest particles known to us, and they transfer the energy necessary for melting of the powders uh, by virtue of attaining high speeds and then colliding with the surface, thereby transmitting their kinetic energy, which leads to the rises in temperature. Now, if the path of this electron beam was to be interrupted with something like other heavier molecules, such as those of inert gases or even just air, there is a chance that these electrons, being very light, will simply get uh, uh, say they will simply collide with these other heavier molecules, whether of inert gases or of air, and they might get scattered away uh, rather than interacting with the metal powders as intended over those small beam spot size. So we will not be able to print any parts should the vacuum of the system be affected. Thus, the path between the electron beam and the target material should be empty, and this can be achieved only by a vacuum. The build platform is typically made from the same material as the powder being printed, or at the very least, it has to be compatible with the powder being printed. Otherwise, we may have effects such as delamination of the part with the build plate, or the formation of some deleterious secondary phases or intermetallics, which is highly undesirable. Also, typically, the build platform has a flat surface. As we see here, electron beam melting or EBM is the commercial powder bed fusion process developed and marketed by RCAM, which is now acquired by GE. And typically it has this top feeding mechanism where you have these two powder hoppers. The rake is what we're referring to as the doctor's blade or the recoater blade. There is an electron beam gun at the top, and the doctor's blade can move in either direction. So, say for one pass, it can start here, travel to the other end to position 2, and spread the powder across the build tank. Then the electron beam gun can scan over the regions of interest. While returning from position 2 back to position 1, it can spread a second layer of powder and the process can complete itself. So rather than going from one end to the other and coming back, it spreads powder in either direction of travel, like a raster scan. And that is obvious because we have two powder hoppers here, which saves us time. In terms of the typical process parameters, especially in the context of machines developed by RCAM, the powers have been used up to 3 kilowatts or 3000 watts. So, in fact, on this is less than what we than what is available for laser beam based powder bed AM machines because those can go up to 10 kilowatts, and encountering machines with 3 or 4 kilowatts is like really common. The currents in this case can range from 1 to 50 milliampere. Scanning speeds can go up to, so I believe a correction is needed here. Scanning speeds can go up to 10 to the power 4 meter per second, which is really high. The input power or input voltage is 150 kilovolts. The vacuum which is required to be maintained here is of 5 into 10 to the power 5 millibar. And if we recall, this is the vacuum which is typically required in the working chamber of, say, any machine like a scanning electron microscope. Whereas in the gun chamber or the chamber where the electrons are actually getting generated, the vacuum has to be of the order of 10 to the power minus 9 millibar or less. The layer thickness which can be achieved and thereby the resolution of the features is between 10 and 150 microns, which is pretty good. As we are well aware, VAT photopolymerization has perhaps the highest resolution or the smallest layer thickness, which is of the order of microns, so some 4 to 5 microns. But this is also good enough. The surface roughness can be between 2 to 20 microns, and the beam dia is typically between 100 and 350 micron. The reason that we do not have a finer or smaller beam dia, which by the way is possible with lasers, is because electrons are charged particles, and if we try to decrease the beam dia too much while keeping the electron flux constant, after a point the charged electrons will start repelling each other, and physically it will not be possible to contain them into a very small spot. Of course, the other way is to decrease the electron flux, in which case the beam dia can still be decreased or reduced. But in that case, there simply might not be enough energy in the incident beam to say build the part or to melt the metal powders. Thus, there is a physically imposed or naturally imposed uh, ceiling on or floor on the what is the smallest beam diameter for such processes. And if we look at the typical process cycle for electron beam building or similar technologies, the first step is the spreading of the powder layer. So in this case, as we can see, this was the height of the last printed layer. Now the bed moved down by an height equal to this. Let's call it h. And then the doctor's blade or the recoater blade is moving in this case as shown from left to right, spreading the powder evenly. And then the electron beam gun will first preheat the entire um, build chamber or the build bed. And as we can see, this is achieved via this relatively larger beam dia, or it can be achieved with a smaller power. The reason for having a larger beam dia is that now we can scan our entire build plate or build region with a smaller number of passes. Whereas if we were to do this with the same beam diameter without changing and just by reducing the power, the number of scans required would be more. Again, because this process is so fast, maybe in terms of time, the difference would not be so much. But typically, this is what is adopted. So either your beam dia can be increased or the beam can be defocused so that effectively the beam spot size on your target surface increases or gets enlarged. Preheating, as we saw, is one of the steps that is useful for mitigating the development of tensile residual stresses. Thus, rather than starting print on a cold bed or a bed that is at ambient temperatures, we tend to preheat it, and this preheating temperature, say, typically can be anywhere between, say, 300 to 600 degrees C, depending on the application and depending on the optimized parameters that you have, and of course, depending on your material and machine combination. After preheating, a fine beam, as we can see here, is used to scan the build region uh, over the regions of interest, and this will print or selectively melt the powder in the regions required. And this cycle continues. Once the part is completed, this entire bed, so this entire build chamber is taken out and the excess powder is removed and the part can be extracted. Now, given that it is metallic powder, we need to exercise utmost care because they are toxic to humans and we should not really breathe them. In fact, we should not even handle them with bare hands. So, utmost care must be exercised. This video also showcased a typical electron beam melting process from courtesy of RCAM, and it just was an animated visualization of the process steps that we just discussed. Now let us take a moment to talk about the manufacturing steps for the metallic powder that is typically used in all powder bed based additive manufacturing processes, or also powder feed based additive manufacturing processes such as blown powder directed energy deposition. I also discussed this briefly in one of the past sessions, but this will be a useful revision. Perhaps the most, say, common or typically encountered way can be pulverization, where we simply crush and grind bulk material to form fine powder. And this crushing and grinding operation is performed mechanically. The powder produced from this process, though irregular in morphology, can be very fine. Also, this is perhaps the most cost-effective method. So if we are not much concerned about the powder morphology, whether it is say spherical or not, we don't care if it is elongated sometimes or if the distribution of powder particle sizes is say varying in terms of morphology. All we want is a cost-effective process which can give us a reasonably fine size of powder, that is very small powder. Then pulverization can be relied upon. The second is electrolysis. So where two electrodes are placed inside the suitable electrolyte, and anode is required of the made of the required metal, and on this anode, further metal will be getting deposited. And being a chemical process, electrolysis can produce very pure powder, such as of iron or copper, and this may be especially suitable for applications where purity is of utmost importance, such as say if you want to make some implants or medical implants out of that powder. Maybe electrolysis is the way to go, as the powder that you'll get will be of very pure quality. However, there is no comment on the size and morphology, so it can be expected that the morphology can vary, and perhaps the control over the size distribution also may not be very strong. Then there are the atomization processes, of which there are two. One is gas atomization, the other is plasma atomization. In either case, the molten matter is converted into droplets. For the case of gas atomization, it is converted into droplets upon being bombarded with a jet of inert gas. So this gas can be either nitrogen or it can be argon. And what happens is when the molten metal is bombarded with this jet of inert gas, it separates into small particles which then solidify into regular and spherical shapes. And again, here you can have, based on your process development, you can have a collection chamber at the bottom, which collects, say, larger particles or coarser particles. And here, a separate chamber which can collect fine powders. And this fine powder can is actually getting carried by the inert gas itself. So particles which are very fine and light can be carried by the inert gas into this chamber, whereas somewhat larger particles which are not light enough to be carried by the gas settle at the bottom. However, since this process utilizes, say, some gas, whether nitrogen, argon, or any other, the particles made from this process are also susceptible to gas intake, and thus the final chemistry of the metallic powder will reflect the gas used for atomization and will be different from the nominal alloy composition. In the case of plasma atomization, however, the molten metal is subjected to a sudden vacuum, and because of being exposed to this vacuum, the melt disintegrates into these small droplets, which then solidify. So this entire process takes place in vacuum. and as such, there is no gas uptake. Thus, the chemical purity of the powders is maintained. And as remarked here, plasma atomization is the best for additive manufacturing processes, and this is also the type of manufacturing method employed by RChem for the powders that it uses. However, as we know, irrespective of the process that we use, we will never really end up with a batch of powder with only one particle size. That is, say, you will never have a batch of powder that has, say, exactly all powder particles are of 60 micron. This is simply physically impossible, or even if possible, the costs will simply be too high to justify this. What you always have is a distribution of the powder particles. Now, this distribution can be controlled. So, say rather than having such a wide distribution, this can be even tighter. And with such increased quality control, the costs will also shoot up. However, the distribution of powder particle sizes, that is, having a batch of powder which has both, say, an average particle size, which is most desired by us, and particles smaller and larger than that average size, has some of certain advantages, as we will see. On the right here is also a scanning electron microscope image of powder particle of powder particles that I presume were used as feedstock for some AM process. As we can see, that they're mostly of a regular spherical shape. Some of them are also elongated, but the overall character appears to be spherical. Let us talk about the focusing and deflection mechanism, because as we know, it is not just sufficient for the electron beam to fall just near or coincident with the optical axis, normal to the build surface. The beam also needs to be deflected across the entire build region. So in most of the electron beam guns, electrostatic field is used for extraction and acceleration of the electron beam, and magnetic fields are used for focusing, deflecting, and correction. So while extracting the electrons from the target or from the cathode material under is usually done under very high voltages, and an electrostatic field is thus used. However, once these electrons are extracted and are freely available, to focus them into a beam and to deflect them all over the built chamber, we use magnetic fields. And the equation 1 also defines these interactions. From the cathode, that is here, where the electrons are extracted from, to the anode, which is the positively charged annular feature shown here, which actually attracts the electrons once they are freely available from the cathode. In this region, the focusing is done by electrostatic force, and there onwards, that is from the anode to the target surface, it is done by magnetic forces. In this first stage, the focusing, the magnitude of the electron's velocity increases due to electric field, and in the second stage, the magnitude of velocity no longer increases, but acceleration is affected by changing the direction of velocity. The distance from the anode to the maximum beam dia is called the objective distance, and the distance from this plane of maximum diameter to the target surface is called the image distance. We also have helpful equations here which can help us predict or determine the focal distance given the other parameters. Now, for your machine or setup, the mass and charge of electron are already, say, natural constants. The width of the focusing coil will be fixed. The acceleration voltage typically also we have say some optimized or well-defined voltages based on the application. And thus we can see that the focal length F varies inversely with the magnetic field strength, square of the magnetic field strength. Now the magnetic field strength itself directly varies with current, so it is also possible to say that the focal distance varies inversely with the strength of the current, square of the strength of current. Such variation is also shown here in this plot. Uh, just a minute. Now let us talk about how the electrons are deflected using these focusing, deflecting, and correction optics. So in an electron beam gun, the electrons are deflected by electromagnetic lenses, which generate the forces as shown here to move the electron beam. Electromagnetic force is equal to Q times V cross B, where V is the total velocity of the electrons, Q is the charge on the electrons, and B is the magnetic field. So for the scenario shown here, the direction of V is to the right. So this is V. And to affect the deflection as shown here by the angle theta, the direction of the magnetic field has to be into the plane of the slide. So that is, it goes into the plane. And now if you were to do a cross product of V cross B, we can see that the cross product will have a direction as shown here, which will uh, result in such a deflection by angle theta from the uh, initial traveling axis. Again, what can be seen is that, say, if the voltage, if the magnetic field is constant over this region, whenever the beam or whenever the electron moves by a small distance, the force acts on it along this direction, deflecting its path by a small angle. Again, the force is acting in the same direction. And this is somewhat analogous to how the centripetal force acts on any particle or any body which moves in a circular path. And so the locus of the path of the electron can be considered to be that of a circle. And similar analogy has been used here to come up with a simple expression for the, say, this length x, which characterizes or determines the deflection of the electron beam when it has traveled a length L. That expression is x equals ALQVB by 2EV, where x is the deflection in meter, L is the beam throw distance, V is the acceleration voltage, B is the magnetic field in Tesla, and A is the width of the constant magnetic field region. So we observed how the deflection can be affected or achieved along one direction. However, when we are scanning a plane, we would need to deflect the beam in a combination of x and y directions. And for such applications, typically such deflection coils are used as shown here, which have four poles, and based on the current supply to these four magnets, the electron beam can be suitably deflected. Again, because of the presence of such deflection coils, which can which have very low latencies, that is, they can, say, start working very quickly, and because of the inherent fast speeds of the electron beams, scanning speeds of the electron beams, we need not always scan along straight lines. In fact, we can scan along such paths as shown here. So maybe a circle of a fixed radius, then displace the center by a fixed distance, come up with this second circle, and so on. Or we can also have this bilinear type of scanning strategy. And often the electron beam moves so fast that it appears as if there are multiple electron beams scanning the region of interest at the same time, when in reality it is just one beam moving very fast. We have also been talking about the issues with the beam when it interacts with the target surface, and how um, the the cross section of the beam or the shape of the beam, when it comes out or the intended design shape is circular. However, when it is deflected at large angles from the optical axis, the effective cross section becomes elliptical, which leads to a change in the distribution of energy. Because of this distribution in energy, change of distribution of energy, when the beam is scanning close to the optical axis and away from the optical axis, the final parts can have non-isotropic properties because of the change in energy density. And such effects can be corrected in this case using stigmators. So stigmators are the electromagnetic coils with multipoles used to correct electron beam shape. And here there can be some additional sources of error, such as misalignment between the electrodes, or there can be some interference between the electric and magnetic fields. We see what the erroneous profiles look like. So they are elongated and elliptical away from the optical center, whereas near the center they are still circular. Whereas for the corrected profiles, we see that even irrespective of whether they are close to the optical axis or far away, the beam cross section is still circular, which can ensure omnidirectionality of properties and isotropy. Now, there are certain challenges in electron beam based powder bed additive manufacturing processes, and some of them are highlighted here. One can be delamination, and this typically occurs when the temperature gradients are very high. That is, say, your bed or the powders are at ambient temperature, and you suddenly start scanning and reach melting temperatures, say somewhere in the neighborhood of 1600 to 1800 degrees Celsius. So, over a small distance between the top of the powder layer and, say, the build plate, you suddenly have a very large temperature difference or a very high temperature gradient. Now, such temperature gradients typically will result in delamination, as can be seen here. So, this delamination can be between the build plate and the first few layers, or it can also be between the layers of the build, such as shown here. And here it is between the build plate and the first layer. Or it can lead to the formation of uneven surfaces, and this is typically encountered when the energy density in the beam is inadequate. Say if you're trying to work with some high melting point or refractory materials, or some refractory materials are alloyed into your metal powder, you may have to use energy beams of higher density or higher wattage, or increase your volumetric or energy density via other means. Otherwise, such uneven surfaces may be observed, and the powder may not melt completely. You may have partially melted or unmelted powder. Then there can be porosity, and as we discussed, porosity can be of two types. It can be either, say, gas induced, which are typically spherical and small. Gas induced porosities are observed because in the liquid state, the metals have a higher solubility for gases. However, when the melt pool is solidifying, the solidified metal has a lower solubility for these gases, and thus in the solid state, the gases are liberated. These gases tend to form these bubbles, which are typically spherical and small, and then they get liberated, leaving these spherical voids behind. The other type can be process induced, and that is what is shown here, because here the chances for gas induced porosities are lower because the built chamber itself operates only under vacuum. There is no flowing gas. However, some gases may still be present if we are using a gas atomized powder stock feedstock. The process-induced porosities are often elongated and irregular. So typically they will be larger than these gas-induced porosities, and also they will have a non-regular irregular shape and they will be elongated. Sorry. The most commonly encountered error or challenge in this electron beam melting process is that of powder smoking. And what happens is it appears as if there is an explosion of powder which blows away the powder from a layer, and because of this the part cannot be built properly in that layer because suddenly there is no powder. This typically happens because, as we know, in this the powder particles are maybe assumed to be spheres, and when you have spheres in contact with each other, the electrical contact across them only happens at these points across very small areas. And as we know, the resistance is inversely proportional to the area of contact. So if the area of contact is larger, the electric resistance will be low. If the area of contact is smaller, the electric resistance tends to be high. Here, because of the sphere-to-sphere contact or the non-conformal contact, the electrical resistance is high. The electron beam, which is bombarding the powder bed, the charge tends to get accumulated in these powder particles. And once sufficient charge is accumulated, the powder particles may suddenly repel each other. And this can lead to this explosion-like phenomenon that is observed. And as we can see, this phenomenon is of the time scale of milliseconds. So at t equals 5 milliseconds, the powder has started to glow. At 10 milliseconds, we see these initial spatter-like streaks. At 15 milliseconds, the powder is still spreading around, and by 20 or 25 milliseconds, we see that it has started to bounce far away from the powder bed. At 40 milliseconds, we see that no powder is left in the affected region. Another set of defects can be due to volume shrinkage, and this is typically because of the phase change from liquid to solid. So when we are having a powder bed or when we are spreading a new layer of powder, it will have a certain packing efficiency or packing density. This is also something we discussed when you're talking about the roller-based recoating mechanism, where we said that if there is a roller has 2 degrees of freedom, one with its related to its translation, the other related to its rotation about its own axis. Now, if we have a forward rotating roller, that is the sense of rotation is also along the direction of its translation, the powder bed tends to be better packed and the packing density tends to be higher. In such cases, the shrinkage due to phase change will be lower because, as we know, a higher packing density implies less voids. Because of less voids, even though there will be shrinkage because of the change from solid to liquid phase, I'm sorry. So the because of the less volume of voids, the shrinkage will not be a lot because typically for metals, the volume does slightly increase when changing from solid to liquid. However, when the melt pool freezes back again, the entire volume is now solid. However, if the packing density is low and there is a large fraction of voids, we can observe the volume shrinkage as shown here in the second diagram. Now, this slide lists some of the common reasons for the smoking phenomena, which is also known as spreading or pushing of powder. Some of the main reasons are the presence of water residue or humidity in powder, which, when heated, vaporized as an explosion. The momentum of the electron, which is greater than cohesive power force of powder particles, and perhaps most importantly, the buildup of electrostatic charge on the powder particles. The reason for such buildup of electrostatic charge is also given. This is typically explained by the pointwise connection between the particles, that is a non-conformal contact, and due to oxide layer formation. Say if your powders were exposed to an oxidizing environment and may have a layer of oxide formed on top of them, their conductivity will be affected severely, and such phenomenon may be observed. Some ways to mitigate smoking are by preheating or say light sintering as done by RCAM, where we scan the entire surface with a larger spot size to preheat and increase the temperature. In some cases, sintering, a partial sintering step may also be implemented. It can be mitigated by changing the process parameters, that is changing the current density, the beam size, and other relevant parameters, and by utilizing better scanning strategies. The typical melt pool profile for electron beam melting process is also shown here, and this can be explained by how the electrons are interacting with the material. So there is a flux of electrons which is incident on the surface. A fraction of them get transmitted from this first layer, which is denoted by eta T1, whereas a fraction will also get backscattered. That is, they will be elastically scattered in that layer and then they will exit the target surface. Now, from the fraction that got transmitted into the next layer, one fraction will again get backscattered and they will get embedded in the first layer, whereas some part will get transmitted onto subsequent layers, and this process continues. Also, we see that the distance of at which these electrons are getting embedded tends to increase before there are no more electrons which can get transmitted. And that is how we get this typical melt pool profile. For a wider electron beam, the corresponding profile is shown on the right, where you have this region of almost uniform, uh, say, melting, and then at the sides you have the characteristic bulge. And here the plots also show the fractions of electrons that get transmitted, backscattered, or absorbed in a particular layer in terms of fractions. And this law is always obeyed. That is the fraction of electrons getting absorbed plus the fraction of electrons getting backscattered plus the fraction of electrons getting transmitted equals 1. So if the layer thicknesses are taken to be some 15 microns, which is the value of dz here, we see that in the first layer, the transmittivity is say almost like 0.25 and the percent fraction of backscatter is say 0.15 or so. Now in the second layer, the transmittivity fraction reaches maybe zero point 0.6 or zero point 0.7, whereas the backscatter fraction increases only by a very small extent. And upon reaching the Sorry, the transmittivity fraction decreased because this scale goes from right to left. That is it is 1 to 0. And upon reaching the third layer, we see that the transmittivity fraction is almost near zero. That is, it has become very small. Only a very small number of electrons that can get transmitted further. And by the fourth layer, this fraction has reached zero, as we can see. Whereas the fraction of electrons that get backscattered has almost stagnated. And 1 minus eta b minus eta t, which is eta a, gives you the fraction which is getting embedded. That may also be represented by this hatched area here. The penetration depth, as we can see, mainly depends on the accretion voltage and the density of the material. Next, let us talk about the binder-based powder bed AM processes. So here again, we'll talk about the working principle and the various subsystems. Then we'll talk about the powder and the ink materials, the scanning systems, the powder delivery system, powder recoating system, and some commercially available machines, those being Z-Corp's 3D printer, X1's sand printing, X1's metal printing, and some very interesting applications in terms of time delivery drugs. So we are here discussing the binder-based powder bed AM. A general schematic is shown to the right here. And as we can see, it is very similar to other powder bed based AM processes. The only change here is in terms of this ink head, which is dispensing the ink. And this is, say, analogous and very similar to inkjet printers that we may have used at home or in the office. And if we just add a z-axis to that inkjet printer, then we will end up with the process that we are talking about. The joining mechanism here is via binder. The powder materials can be any, so that we can have ceramics or metals or polymers or maybe even more. The scanning system is actually by this uh, ink head, which scans over the surface. The powder delivery system is can be either a top feed or bottom feed. Powder recoating again can be either a recoating blade or it can be a roller or it can be a slotted feeder. The build atmosphere is neither purged inert gas nor vacuum because one of the strengths of such processes is that they occur at ambient temperatures. So the powder is not really exposed to oxidizing conditions. Neither are any dangerous fumes released, nor is there a need to maintain vacuum as there are no electrons or electron beam in this case. So often these machines are open to the atmosphere. The build platform requirements are similar to what we discussed previously, that is, they should be compatible with the material that we are working with, and they should not lead to unnecessary delamination or the formation of any secondary phases. It, in some cases, it may also be required that the build platform is flexible for easy removal of the part. So as we discussed, the powder and ink material can be ceramic, polymer, metal, or multi-material. Scanning system is based on the print head and it can consist of a single nozzle, which is just like a theoretical case because almost always they will have multiple nozzles. The powder delivery system can be top feeding and bottom feeding. Recoating can be done via blade roller or slot feeder. And even whether it is a single nozzle or a multi-nozzle, it can in turn have either a continuous delivery system where the drops are following continuously, or it can have a drop on demand system where the drops are dispensed selectively. For binder-based powder bed AM processes, a wide choice of powder and binder materials and their combinations are available. The binder can also be mixed with other materials. Further, different materials in terms of color or properties can be dispensed by different printing heads. Therefore, binder bed powder bed AM can exercise control over local material composition as some 30 to 50% material can also be mixed in the binder and dispensed over the powder bed. The material can be in liquid carrier or it can be applied as molten matter. The proper placement of droplets can be used to create surfaces of controlled texture and to control the internal microstructure of the printed part. And such processes have unique flexibility. They can create parts of any geometry and out of most materials, including ceramics, metals, polymers, and composites. Further, they can exercise local control over the material composition, microstructure, and even the surface texture. These processes are also readily scalable in production rate through the use of multiple nozzle technology, which has been commercially developed. The material and binder combination can be categorized as shown in this slide here. So depending on whether the binding component is available in the ink or whether the binding component is already present in the powder, such as say in the case of starch or cement, where dispensing water, where we dispense water to bind the materials, water itself does not have any additional chemicals which act as binder. The binding character is present in the powder itself. It is just activated by that water. If there is some binding component in the ink, then the combination can be by using ceramic metal or polymer powders in conjunction with inorganic or organic ink. If the binding component is already available in the powder, then we can simply use either aqueous inks in a conjunction with starch, cellulose, plaster, or ionomer cement powders, or we can use some solvent inks in conjunction with polylactide and polycaprol acetone powders. As we were discussing, uh, irrespective of whether we are using a single nozzle or whether we are using multiple nozzles, the ink can be dispensed from them in two ways. Either the ink can fall continuously like a curtain and the head can scan over the printing bed, or the drops fall in a drop on demand fashion where they're dispensed only in the regions where required. However, as we can obviously tell, the continuous falling of the droplets is not really desirable because what happens when we are scanning over regions where we don't want the material to get bound? In such cases, um, things have been in ways have been engineered, such as shown here. So here we have this cup, which is nothing but a reservoir for storing the ink. In such case, the ink is previously electrostatically charged. So it can be given a suitable negative or positive charge. The cup will have the opposite charge. And when the we are scanning over a region of interest, this cup is kept far away or the cup is deactivated, as in its charge it is switched off. So the bead, the ink falls normally downwards. And when the we are scanning over a region where we do not want the binder to fall, we can activate this cup and that will deflect the path of the electrostatically charged drop of ink and it will get attracted towards the cup and get collected in it. Later, this ink may also be possibly utilized after some post-processing. So it is not completely wasted. In some cases, however, it may not be possible to utilize the ink and then it has to be discarded. And this is also illustrated very well by this signal diagram here, where the drop ejection signal is continuous. There is no change in it irrespective of the region that we are scanning, whether it is a desirable or undesirable region. However, for the undesirable region corresponding to these three pulses, there is this activation of the drop deflection signal, which activates the cup, and the drops fall into the cup rather than falling on the powder bed. In the drop on demand situation, however, we only are dispensing the drops of ink in the regions where they're required, which corroborates to these two pulses over here. So in between, there are no droplets, which would have been the case if the drops were getting indiscriminately dispensed continuously. But how is this drop on demand phenomenon achieved? So there can be two ways. They can either be achieved by thermal means, in which case you have this plate. The plate is heated, and upon heating of the plate, the ink or binder in its neighborhood gets heated, and it may be possible to heat it to a temperature so that uh, the ink vaporizes. That leads to the creation of this bubble, and this bubble displaces an equivalent volume of ink out of the nozzle, which falls below on the surface. This is a thermal head. A piezoelectric head uses a piezoelectric, which we know when subjected to a voltage will suffer a deflection. Now, because of its deflection along the directions shown, there is a change in available volume for the ink inside this nozzle, and thus a small volume of ink is displaced out of this nozzle and falls on the binder bed, sorry, on the powder bed. There is also this helpful comparison of the thermal head and the piezoelectric head. In terms of cost, the thermal head is more cost effective. Also, it has a higher printing speed compared to the piezoelectric head. However, because of the way in which the thermal head works, it exposes the ink to high temperatures, and thus the binder can be exposed to higher temperatures and correspondingly higher thermal stresses. Whereas the piezoelectric head does not really raise the temperature in any way, so there is no thermal exposure. And as we remember, one of the greatest strengths of this binder-based powder bed AM processes is that they are performed at room temperatures. So there is no scope of high temperatures or any thermal stresses resulting from high temperatures. The drops that are dispensed from a thermal head typically tend to have a non-uniform size, whereas a piezoelectric head is very consistent and reliable in terms of the droplet size that it dispenses. Again, the thermal head dispenses droplets which do not really have a strong sense of directionality, as in, it is not necessary that they will fall normally downwards. It is possible that the drops may get deflected, whereas in the case of piezoelectric heads, there is a high directionality of the droplet. So as we can clearly see, the piezoelectric head, though relatively slower, tends to give better quality control over the part. So if we are not really concerned much with the, say, the maintaining the geometrical accuracy, or not concerned, or our tolerances are very relaxed, we can rely on a thermal head. Whereas if we want to print very fine features with small tolerances, we should use a piezoelectric head. The powder feed system, as we spoke, can either be a top feeding or a bottom feeding type. So here a bottom feeding mechanism is shown, but we may equally have a top feeding mechanism where you have this pair of hoppers, and the reason for having these hoppers is also because it tends to decrease the overall size of the machine and the chamber. And we can clearly see how that would be useful in an electron beam melting light process because we have to maintain vacuum over that entire chamber. If the size of the chamber is very large, achieving vacuum will take a very long time, as well as there will be many vulnerable points from which leakage can occur and that vacuum can be disturbed. Whereas with a top feeding mechanism where we have this pair of hoppers suspended on top, which dispense the powder, the chamber size can be greatly reduced. Thus, our machine will have a smaller footprint in the XY plane. The recoating system, as we discussed, can either be just a doctor's blade, which is like a two-dimensional lamina which scans over the powder bed and can spread the powder uniformly. The advantage is that it can handle large quantities of powder. That is, if you want to build with very thick layers or if you want a high build rate, you can use a doctor's blade. On the other hand, the rollers, though not capable of handling very large quantities of powder, have 2 degrees of freedom. So here the degree of freedom was only one. In this case, you have 2 degrees of freedom, one corresponding to translation and one corresponding to the rotation. As we already know, if this is the direction of travel, the first case is a forward rotating because the sense of rotation also corroborates with the direction of travel, whereas the other case is that of a counter rotating roller. The forward rotating roller tends to compact the powder, so in this case there is a greater compaction, and resultantly there is also a greater packing density. Whereas in the case of the counter rotating roller, where the powder particles are pulled up and above from below the powder bed, you can have better flowability of the powders. So in case you're working with powders which are not very flowable and they are difficult to spread out in the form of a layer, you can work with a counter rotating roller. Of course, a separate class of recoding system consists of this slot feeder mechanism, which is also commonly used in this binder based powder bed AM processes. Now, depending on the combination of the subsystems, we have the different machines. So one of them, perhaps the most famous, is Z Corp's 3D printer, which was in fact developed by MIT. The working principle is very similar to SLS, except that the binder liquid is sprayed in selected regions instead of laser. The raw material is powder, and prototypes or concept models can be prepared rapidly using a multi-jet, multicolor spray over starch. The green parts will, however, require sintering inside another furnace. When a binder is sprayed through thin nozzles on the selected region over a layer of powder, the particles in that region stick together. The remaining powder then acts as the support. Binder sprays make use of the mechanical movement. However, use of multiple jets makes it faster. Explicit support structures are not required. And also in this case, since we're not really exposing the powders to high temperatures, the chances of warpage are also very low. So we do not even require explicit supports to prevent warpage. Thus, supports are totally eliminated in this case. Of course, the overhanging features can be prevented from drooping under the effect of gravity by the surrounding loose powder. And as we already saw, a wide variety of powders can be used, whether they are metallic powders, ceramic powders, or polymeric powders. And this is the first technology that was given the name of 3D printing because it was very similar to the inkjet printing methodology. Z-Corp was founded in December 94 um, by Marina H., Walter B., James B., and Tim A., based on a technology developed at MIT under the direction of Professor L.E.S. And some specifications of the Z printer 15250R. resolution in terms of DPI, 300 into 450 DPI. This resolution is similar to your is defined similar in a fashion to 2D printing, dots per inch. The minimum feature size or the Z resolution is 0.4 mm. The vertical build speed is 20 mm per hour. Build size can be up to 236 into 185 into 127 mm. And typical materials that were used were starch and plaster formulations. And we see these colorful objects here. That is because for binder-based powder bed AM processes, the color is not only on the surface, the color can get all the way through the bulk of the part, and this can be done achieved via the using the binder of different colors. The next technology is the sand printing technology by X1, and X1 has also developed the metal printing technology. Now, a very interesting and perhaps very important uh, application of this binder-based powder bed AM process is something called the time delivery drug. So, binder bed, binder-based powder bed AM is a suitable process for producing time delivery drugs, and this is because this is the only process which dispenses materials from two different sources. As we discussed, 30 to 50% material can be dispensed from binder, and 50 to 70% material is contained in the powder bed. So inherently, there is a very strong capability for producing multi-material objects. Therix USA is the pharmaceutical company which produces these drugs this way. However, in principle, any deposition process with the ability to control flow rate of multiple materials can be used, such as powdered ED. The rate of dissolving is proportional to the surface area of the tablet. So, the concentration of the drug should not be distributed uniformly because in such a case, what will happen is that, say, if this is the percentage drug release and this is your time axis, with time, the surface area will decrease, and so the percentage drug release will also tend to saturate. Maybe it will take on a characteristic such as this. So initially, you might have in the same time step might have a good release of drugs, whereas later, once this saturates in the same time step, the amount of drug released is very small. And this is undesirable. However, this is mostly the case because the drug compound is distributed uniformly in the pill, and the rate of dissolving of that pill is proportional to the surface area of the tablet. The greater the surface that is dissolved, the greater the amount of drug released. However, such uniform distribution is not really useful, and what we want to aim for is something like a linear profile, because in this case, for equal time steps, equal amount of drugs will be released. In conventional cases, the concentration of the drug shall be distributed such that the specified rate of drug is proportional to the conformal area. Based on this consideration, the concentration at conformal layers is in close intervals is decided. In the case of these new engineered drugs, what we can have is instead of having a uniform distribution in the pill, we can have these contours of concentration where we can have higher concentration in the center, and as we move out, The concentration can be suitably reduced because, as we saw, larger surface area is available initially for dissolution. So even if the drug concentration is lower, the product of the drug concentration and the more greater surface area may lead to equal amount of drug release. Whereas when we move towards the center or as the pill gets progressively smaller, a smaller amount of surface area is available for dissolution. So we should have a higher concentration to maintain the same rate of drug release. Now this geometry is then sliced into multiple layers and then printed using such a binder-based powdering process. The resulting gradient geometry is sliced into horizontal layers, retaining the information of the relative concentration of the drug in the matrix. Then the drug is dispensed from top of the surface of the matrix layer each time. In each layer, where the drug is dispensed, its flow rate is controlled so as to get the desired concentration. Also, as you can see, this while this phenomenon is known as sustainable release or sustained release, this can also be leveraged for multi-drug release where you make a pill which has one drug on the outside and another drug contained inside, which only gets activated once this outer drug is sufficiently dissolved. And its characteristics can look something like this. So initially you can have drug 1, and once this starts to almost saturate or ends, you have the release of drug 2. As we know, for patients who need to take a large number of different pills, it can often be very confusing and it can be a bad experience because they have to take so many pills. Sometimes they may also forget or there might be mistakes in taking these pills. So if you can integrate these multiple drugs into one single pill that the patient has to take, it will lead to better user experience for the patient as well as it will ensure that all the necessary drugs are taken on time and the patient can recover uh, well. So that was a review of the contents covered. We'll take a short break now, and when we return, we'll look at some conceptual problems which will help strengthen our concepts and help us in solving the assignments for this week. So let us take a short break. Welcome back. Let's continue. Now, as binder-based powder bed AM is not one of the processes which is, say, more commonly discussed or more commonly available, especially in academia. I looked up a few papers and I found this really nice paper by Mustafi, who have outlined or reviewed some of the important aspects of this process. So let us also quickly go over it. Here is a schematic of the process, starting with the which shows the complete process cycle when building a part, including the build and the post-processing steps when building a part using binder-based powder bed process. So the first step, as we just discussed for so long, is how the print head selectively dispenses this ink onto the powder bed, as shown in this step here. Then this entire the part can be then sent into a furnace for low temperature curing at approximately 200 degrees Celsius. And then these low temperature cured parts can be separated from the other parts. Then they can from the powder, and this process is called depowdering. Now the cured parts are set up for infiltration because here at approximately 200 degrees, it is expected that the binder would also have evaporated and leaving voids behind. And these voids, if they continue to exist, will weaken the part. And during any structural application, these can be the regions where cracks, say, initiate or tend to uh, form. And so these voids must be filled up. And typically, this is done with an infiltrant material, say bronze, as shown here, or in some cases, copper is also used. It is set up for this infiltration process and again sent for sintering. However, this time it is a higher temperature. This temperature is sufficient to melt bronze or copper, but lower than the melting point of the build material itself. And under this high temperature, the infiltrant material can permeate into the voids using by the means of capillary action and can fill the voids. Finally, the runners are removed and the final parts are obtained. As we can see, the final parts will in fact be a multi-material of the build material powder and this infiltrant material. And unlike PBF technologies, that is metal PBF, the binder jetting is compatible with virtually any powdered material. And because numerous powdered metals and ceramics are sintered to full density, binder jetting has a real potential to surpass PBF and have the widest selection of materials for all AM processes. Again, as we discussed, this process occurs at room temperature and also the normal open atmosphere, avoiding issues related to oxidation, the formation of tensile residual stresses, segregation of elements, and phase changes, making the powder around the parts of the build box highly recyclable. If you remember, during our discussion for uh, say laser-based or electron beam-based powder bed AM processes, we discussed how while there is still a chance to recover and recycle the loose powder surrounding the parts, in those processes, because of the high temperatures encountered, these powders are also exposed to the high temperatures by being in neighborhood of the parts. And upon encounter with these high temperatures, so this is in a sense is a form of in situ heat cycling or heat treatment. The thermal cycles can permanently change the metallurgical properties of the powders. Thereby, they may not be directly recyclable, and even when recycled, the properties will be different from the nominal alloy. However, in the case of binder jetting, because high temperatures are not encountered, the powders become highly recyclable. Again, Since there is no requirement for vacuum or purging with inert gases, the build volumes of the binder jetting machines is among the largest compared with all AM technologies and can go up to 2200 cross 1200 cross 600 mm. And while the build chamber is very high, allowing for building large parts, the high resolution is still maintained. Other important features of AM processes, such as the maximum size, the complexity of the produced part, production times, and part qualities, such as dimensional accuracy and defects of the final product, are also preserved. Again, in fusion-based AM processes, support material must also be produced alongside the part. However, in the case of binder jetting, or in fact in any powder bed-based process, the part is supported by the loose powder. Again, because of the high temperatures in the fusion-based AM processes, there can be tensile residual stresses remaining in the final part. However, in binder jetting, while some heat is used for lightly curing the binder, this heating is minimal. Thus, because no significant heating or melting occurs, binder jetted parts do not normally experience thermally induced stresses and distortions. Again, the binder jetting has high production rates and can also, as we just discussed, produce large volume of parts more cost effectively. Some geometries and fine features are better suited for binder jetting than PBF or other technologies. Again, even in terms of porosities, various densities with controlled porosity in terms of shape and size are achievable using binder jetting. And also, as we discussed, it has the capability for multi-material EM, which is not really possible in other powder bed-based processes, because in that case, your powder bed is mostly made of one homogeneous material. If you were to incorporate a second material by any means, the powder will not become, will simply lose its recyclability. Whereas in binder jetting, there is a chance or probability of introducing a second material using the binder. The main drawbacks of binder jetting process are also listed here. One being that it is a multi-step process in which post-processing steps such as curing and densification are required, as we just saw. The as printed parts from binder jetting show lower relative density, approximately 50%, and densification from this state usually results in significant distortion of the geometry. Further, compared to some other PBF processes, the surface roughnesses and can be higher while the resolution may be lower, and the development of post-processing strategies is still a work in progress for a majority of the materials. Now, we already discussed about the powder morphology, but let us just take a quick look again. So morphology or shape of the powder determines both the flowability and the spreadability, along with the natural packing and packing density of the powder. The powder in combination with the roller, if employed, and the binder dispersion then affect the density and consistency of the preform or the as-built part. And while spherical particles have been historically used for flowability and spreadability reasons, powder production using water atomization, powder attrition or pulverization and milling is less expensive and so can also be explored. Highly irregular powders, such as water atomized powder, do not pack well and have much less powder to powder contact, which can lead to higher resistances, thereby making the sintering of these powders a challenge. However, in terms of the printing process, the use of a counter rotating roller means that irregular shaped powder, such as angular ceramic powders, can also be shaped using binder jetting. So this is a good example of using the spreading mechanism in conjunction with the process for processing previously difficult to process materials. Mean size and distribution are two properties that also affect powder flowability, packing density, powder binder interaction, and layer thickness. I'll just highlight these: powder flowability, packing density, powder binder interaction, layer thickness, binder saturation, and centerability. Overall, smaller powders center better while larger powders pack better. There is also a minimum size of powder which can be processed using binder jetting, which is approximately 5 micrometer. Now, segregation is a separation of different sizes of powder in a mixture and is likely to occur in various steps, including during feedstock preparation, the feeding of feedstock into the printer, where the larger particles can settle towards the bottom while the smaller particles can get segregated towards the top, spreading the powder over the build area using roller. And some of the influential factors on segregation include the material, the handling, the operational and environmental parameters. While handling powder to refill the reservoir, the powder must be remixed. Because two powder splitting methods are available, including oscillation of hopper. So the hopper need not simply dispense the powder under the action of gravity. It can also be subjected to an oscillatory or vibratory motion, followed by roller compaction and a powder dispensing method using a roller. Powder segregation may occur in the build box area, in which the former spreading technique results in lower powder segregation. There is also a section on numerical modeling of such processes, which is very interesting. So the numerical modeling for binder jetting process is still in its infancy, and this provides a great scope and opportunity for future researchers. A variety of challenges need to be tackled to enable more efficient and reliable simulations to assist the scientific understanding and engineering practice of this process. Perhaps the most important being the modeling of the powder spreading itself, and this is typically accomplished using the DEM method, or the discrete element method, or discrete element modeling, depending on what you want to call it. DEM has been widely used to predict the powder splitting process. The models, after certain calibration, can provide reasonable predictions regarding the general powder behavior during spreading, as well as the packing density and surface roughness of the final powder beds. However, a better understanding and more sophisticated models are still needed to capture the particle-particle interaction, especially for the powder with non-ideal surface condition, such as oxidized or electrically discharged powders, because as we know, for simplifying the simulation, we typically assume them to have a rough spherical or at best an ellipsoidal shape, because those are mathematically tractable. The effect of these conditions on the surface material properties and hence the particle-particle interaction forces should be well understood and captured. Then there is the aspect of modeling of binder-powder interaction, whereby the current models for the dynamic wetting have been primarily focused on planar surfaces. As the powder size used in the binder jetting process is usually on the magnitude of micrometer, the powder surface curvature is very large. These models originally developed for planar surfaces may not really be very accurate and suitable. Now, whether those strategies for the planar surface apply to the very curved powder surface is unclear. Systematic investigations are needed on this topic. Secondly, the powder rearrangement and spattering driven by the binder impact is a critical physics that affect the green part quality, and this should also be considered to faithfully reflect the actual dynamics. Thus, more comprehensive models are needed to incorporate the liquid driven particle motion, which may be similar to granular flow. And then there is the modeling of the sintering phenomenon. And although phase field method provides a powerful approach to simulate the kinetics of the powder densification and grain growth during the sintering process, the phase field formulation should be definitely improved to be more thermodynamically consistent. Specifically, the free energy density function and the relevant model parameters should have more explicit physical meanings and can be directly related to the actual material properties. So some of these parameters may be very abstract and may not really have a direct physical analogy or a physical explanation. A more physical feel of the process will help us in better understanding and modeling any given phenomenon. Besides, the debinding process before sintering is an important step, and the residual binder on the powder particle surface can introduce noticeable changes on the contact condition surface properties, which can have a significant impact on the overall densification and sintering kinetics. Thus, the debinding process can be particularly important for the sintering of the binder related green parts, which contain a considerably higher volume or weight percent of the binder compared with the green parts. And there are some other aspects of powder quality, such as powder safety, which I also briefly mentioned during our session. And that is because powder materials have a high surface area to volume ratio, requiring extra attention when being handled because they can become explosive. Flammability and explosivity are two key events to be aware of when working around powders of any kind. Even food grains become combustible when in a cloud, which is why many explosivity safety standards exist in food grain processing facilities. Now, while binder jetting has traditionally used non-reactive metals, and the equipment design reflects that, changing to reactive metals should prompt a safety assessment of the equipment to be used safely. Facility and personal protective equipment, however, should be borrowed from prior experience. Further, the move to smaller particles demands attention for the prevention of dust clouds, inhalation, and absorption via the skin. Second aspect is the reactivity of the powders, where metal powders has a high hazard potential due to the high burning temperature and energy output upon combustion. And this very good example of solid rocket fuel, which is made out of aluminum powder. Each metal has a level of reactivity related to its composition in powdered metal, has a reactivity associated with size distribution as well. Now, depending on whether the powder is settled in a pile, it is being moved, or whether it is dispersed in the form of cloud, the reactivity potential can change drastically. And certain safety standards are available for testing to determine various values, such as NFPA 484 Chapter 4 Part 4.3 for determination of combustibility and Part 4.4 for the determination of explosivity. Now, let us look at some questions from this week. Question 1 is asking us, why is a top feeding powder delivery system used in popular electron beam based powder bed AM? And let us examine each of the options one by one. Option A, is it to limit the chamber size? Option B, is it to ensure that vacuum is reached in a reasonable amount of time? Option C, is it because top powder delivery system produces more uniform powder layers? Or option D, is it both A and B? So as we have been discussing, using the top feeding powder delivery system often results in smaller chambers because the hoppers tend to be um, say of smaller dimensions and more tractable compared to this reservoirs of powder that feed powder from the bottom. So option A is indeed true. Now, when the size of the chamber is limited, uh, by using this top feeding powder delivery, there is a smaller chamber volume over which vacuum should exist. And there is also a lower chance of leakages. Hence, vacuum can also be achieved in a more reasonable time compared to a scenario where you have a very large build chamber, and there are more susceptibilities to leakages, and achieving a reasonable amount of vacuum, which is of the order of, say, 10 to the power minus 5. So 5 into 10 to the power minus 5 millibar can take a really long amount of time, and this time, mind you, will add to the production times. Top of powder delivery system produces more uniform powder layers. So as we know, the uniformity of the powder layer does not depend on the powder feeding mechanism, rather it is dependent on the powder characteristics in terms of the size distribution, um, the morphology of the powders, their flowability, and it depends on the powder spreading mechanism, whether we are using a doctor's blade or we are using a roller. If roller, what kind of rotation we are using, whether it is a forward rotating or counter rotating roller, and so on. So option C is not generally true. Thus it is both option A and B. Question 2 is asking us, why are regular spherical shaped powders preferred for EB based powder bed AM? Is it because spherical powders have improved flowability? Is it because spherical powders tend to produce a uniform layer thickness after recoating? Is it because spherical powders are easier and perhaps more economical to produce? What can it be? So, from our assessment of the lecture contents as well as the paper, which I briefly discussed, we know that spherical powders do have improved flowability compared to other irregular or elongated shapes. And because of this good flowability, spherical powders also tend to produce a uniform layer thickness after coating. However, to have these spherical type of particles, we need to resort to more sophisticated means of powder production, which leads to increase in cost and difficulty of process. So neither are they easier to make, nor are they more economical. And as we discussed, we never really have powders of one unique size. More often than not, they will be distributed often along a bell curve. So this can be the frequency or any similar metric, and this can be the size. And we also discussed how you having distribution of particles rather than having particles of only one size is useful, because say if you have particles of multiple sizes, say if you are large, then you have some intermediate particles, then you have some small particles. Then overall, you may end up with a better packing efficiency compared to having um, particles spread across a very narrow distribution. However, in terms of this in for this question, both options A and B hold true. The third question is asking us, why is the scanning speed in electron beam based powder bed AM systems up to 3 orders of magnitude higher than in laser based systems? If you remember, that is how it was. It could go up to 10 to the power 4 meter per second. And let us examine the reasons one by one. Is it because the galvanometers used in the laser-based systems have low but significant inertia, whereas there is no inertia in electron beam-based systems? Is it because galvanometer mirrors are rotated using, sorry, they should be motors. Whereas in EV-based systems, electromagnetic coils deflect the electron beam dynamically. Is it because EV-based powder bed AM is a more advanced and recent technology compared to laser-based AM systems? So, as we have been discussing, laser-based AM systems use galvanometer, which is just a combination of motor-mounted mirrors, and due to the rapid movement of the motors, the laser beam can be deflected all over the build area. However, while the inertia of the galvanometer is low, it is still significant. It's not negligible. However, as we just saw, in electron beam based systems, the deflection, correction, and other processes focusing happens through either electrostatic or magnetic fields. So there is no physical or mass inertia involved. So it is faster. So option A is true. In a similar tone, because of the use of electromagnetic coils that deflect the electron beam dynamically, this is definitely a faster technology than using the motors using galvanometers. However, the recency or the say advanced nature of e-beam processes did not really account for the faster scanning speeds. In fact, electron beam melting may indeed have been founded before these laser-based powder AM processes became common. So it is both options A and B. Question 4 is asking us, a student proposes the idea of blown powder reactor energy deposition using an electron beam as the energy source. What advantage will this technology provide over laser-based blown powder directed energy deposition? Will it have a lower cost? Will it lead to improved production speeds? Will the finished parts have lower porosity, or will it not offer any advantage over laser-based powder, blown powder DET? Now, before comparing the various aspects of the two processes, if we carefully notice the question, it says, student has proposed the idea of blown powder directed energy deposition using an electron beam as the energy source. A blown powder DED process would imply that a carrier gas has to carry the powder into the chamber at the least, and there will also be other uses for that blown powder or inert gas in terms of shielding the optics, in terms of shielding the milk pool, and so on. Thus, there will be a significant amount of gas that is getting blown into the chamber. However, as we discussed, when we are using an electron beam as the energy source to prevent the electron beam from getting scattered and to ensure that it is able to uh, hit or irradiate the target surface, we have to ensure that the electrons in their path do not come in contact or do not collide with other heavier molecules. This is the reason why we maintain vacuum. So it is not feasible to have a blown powder DD process using an electron beam because your electron beam will simply get scattered away. So none of the above are true. Question 5 is asking us, why do binder-based powder bed AM machines typically have no atmospheric control? Is it because of the low process temperatures? Is it because of the low to none chance of oxidation of powder particles? Is it because addition of vacuum system will increase the machine and process cost? Or is it because of a combination of a few reasons? As we discussed, during the build cycle itself, the binder-based powder AM machines are subjected to low temperatures. The post-processing may be performed at considerably higher temperatures. Say the binder burn-off is performed at 200 degrees Celsius. Infiltration will be performed at the melting point of copper, so 1000 degrees or so. So while those processes are indeed significant in terms of temperature, The build process itself is performed at a low temperature. Again, because of the low temperatures during the building cycle, the chances of oxidation of the powder particles again is a minimum. And because of these reasons, the vacuum system is not really needed for this process. And so there is no need to add it. Had it been essential, like in the electron beam based systems, we would have added the vacuum irrespective of the machine and process cost, but here it is just not needed. So both options A and B are correct. Question 6 is asking us, what are the advantages of binder jetting over other additive manufacturing processes? No residual stresses, no requirement of support structures, no need of environmental control, and a wide variety of materials can be processed by binder jetting. And any combination of these reasons can be true. So let us evaluate them one by one. Are no residual stresses encountered? This is true because, as we discussed, the process temperatures during the build process in binder jetting are very low. This does not provide any scope for the buildup of residual stresses, either tensile or compressive. Second, no requirement of support structures as the loose powder acts as a support, and because of a lack of residual stresses, there are no chances of warpage as well. So this is also true. No need of environmental control as we just discussed in the previous question, and that is because this process is carried out at room temperature and room environment. So atmospheric control is simply not needed. And as we saw, this binder jetting process can be used to process a multitude of materials ranging from metals to ceramics to polymers and even multi-material combinations of all of these. So a wide variety of materials can be processed by binder jetting. This should also be clear by our discussion of the paper by Mostafi, which highlighted some of these aspects really well. And as such, 1, 2, 3, and 4 all are correct. And so all of the above options hold true. And that was it for this session. Thanks for tuning in. And it has been a great experience assisting in this course. This was week 12, and we are done with the course contents. There will be one additional lecture next week, which will be like a summary session, where we will either try to summarize all the contents that we have covered over the course of these 12 weeks, or we may try to look into some other interesting aspects of additive manufacturing, which are not explicitly a part of this course. So once again, thanks for tuning in this week and every week since. It was my privilege to assist you in this course. And that is it. I am Sourav Goswami from IIT Bombay. Thank you.